Right, so in this example, I just wanted to talk through some of the spatial analysis examples that were included in the course. Now, for the other notebooks related to like NumPy and Pandas and Basic Python and Scikit-learn, I actually pulled up the code in a notebook and ran it and talked through it. I decided not to do that with this section because some of these processes actually take a while to run because we're working with like geospatial data and whatnot. So instead, I'm just gonna go through my output web page here and talk about some of the code. There's not really a whole lot of different information here other than just reading through it. Some people would prefer to listen, so this is just another way to interact with the content. Okay, so excuse me. So if you want to use Python to do analysis of geospatial data, there are different options. In the like commercial environment, a lot of people use ArcPy. I'm a big fan of ArcPy. I use it in my own work, but we don't talk about that here because we're focused on open source. But ArcPy is really great. It's also really well documented. So if you have access to it, you have an Esri account or whatnot, I definitely recommend learning some Python and jumping into ArcPy. It's really powerful. So what we're going to focus, though, on is the open source stuff. So we're going to look at GeoPandas. Now, GeoPandas is basically an extension for Pandas that allow you to work with geospatial data. So basically, it's a table, and the geometric information is stored in a column in the table, so you can treat it like a pandas data frame. Now, this package does require some extension or some other libraries to work, including NumPy, Pandas, and Matplotlib. You also need Shapely, Fiona, PyProj, MapClassify, and Descartes. So again, setting up some of these geospatial packages is going to be kind of frustrating because of the dependencies and versioning and whatnot. Rasteria is used to read in raster data. So here's a website here for Rasteria. So a lot of geospatial raster stuff is based on top of Rasteria, and Rasteria sits on top of GDAL and then also NumPy, right? So, raster is basically an array. So this allows you to bring in your geospatial data and then treat it like a NumPy array. And then a few others contextually is used to read in raster tile layers, like if you want to add a base map to a plot, like a matplotlib plot that's showing a map. EarthPy provides some functionality that's kind of based on GeoPandas and Rasteria for working with geospatial data and satellite images. I just have a few examples with that. Again, here's a link to its documentation. It's fairly new, so it's still being developed. The major tool that we're going to look at for just doing like spatial and like geoprocessing and spatial analysis is Whitebox Tools. So Whitebox Tools can be ran as standalone in a graphic user interface, but you can also run it through Python. It can also be accessed in QGIS and R and through a command line interface. Excuse me. So here's the page for Whitebox Tools. Now with this, if you want to use it in Python, there are some there's the install and the use of this is a little bit different. So I believe I talked through that in one of the setup videos. Okay, so let's talk through that. So again, here's all of our imports. Again, make sure we can do plots in line. Now this whitebox tools, this is basically linking to the Whitebox tool library of tools, and basically I have it in the same path as where my Python is, and thus it can see it without any issues. So that's all of our imports here. So here I'm reading in a shapefile. So I gave GeoPandas the alias GPD, so GeoPandas, and this read file can read in a vector file. So reading in a shapefile, and then we applied this plot method to it, and that spits back the plot. Now, this is the base plot. These are all the counties in West Virginia, so it's drawing all the vector data with its vertices and everything. And then the axes are actually the units relative to the coordinate system. So this is reference to UTM 17 North, so it's a Universal Transverse Mercator Projection. So this is the easting, and then this is the northing. So that's what that is. Here I'm just printing back the head here, which is just the first few records. Now note what this is basically is a pandas data frame, but note at the end here we have this geometry column which stores the geometry information, and I believe it's in like a tuple type object. So these are all like the coordinate pairs, the XY coordinates with it relative to the projection that define all the different polygons and shapes. So effectively it's just a pandas data frame with the geometry information stored in a column. There's some additional information you get when you whenever you read in geospatial data. So here I'm getting the CRS, or coordinate reference system information. Excuse me. So this is the name of the system. It tells you the units, so it's easting and northing units in meters. The area of use, so it's North America between these longitude values, Canada, US, the bounds of the projection there, and then here's its name. It's a transverse Mercator method, the datum, and the ellipsoid, and the prime meridian definition. Right, so this is all the info about the CRS, or the coordinate reference system. Note this EPSG code, that's the European Petroleum Survey Group code, and those are always unique codes that define different projections. Here again, I'm printing the bounds. So this is like the bounding box, and I just print the first set of records here. Yeah, so if you do bounds, basically what that does is it gives you a bounding geometry, a bounding rectangular extent for every object, every separate object in the data set. So I get a separate bounding box for every county in this set of counties. Now if you do total bounds, what that does is it gives you a single array representing the bounds of the entire data set. So if you want to get a bounding box for each individual feature, it's bounds method, and if you want to get back the total boundary, it's total_bounds method. There. Well, I guess this is our method. These are just properties. These are just properties associated with the layer, so they're stored in when it's read. Okay, and then just to show you just a couple quick like analysis type processes here. I'm writing the centroids of the counties out to a new object and plotting those as points. So these are the centroid points for each county. Here I was trying to make a point about projection. So if you are a GIS user and you work a lot like in ArcGIS or even QGIS, those software tools are good at doing like projection on the fly, which means if you read a layer in that's in a different projection than the map, then it's going to automatically just reproject it, and so it draws at the correct location, on the Earth. Now, a lot of other tools are not that sophisticated. So, for example, here I am reading in a base map and plotting that underneath of the counties here, and you can see that these don't line up, and the reason is excuse me, is that this West Virginia data is projected into UTM 17 North, whereas the base map that I draw in is projected into like a Web Mercator projection. So because they have different projections, they don't draw they don't overlay correctly. So in the second example here, I convert the West Virginia data into Web Mercator, and then I plot it, and then they line up correctly. So that's something you generally need to be more careful about when you're working with geospatial data. You need to if you're using these open source tools and code, my general rule of thumb is I want everything to be in the same coordinate reference system or projection or whatnot. So I know that there's not an issue. And if you need to do that, you can do it using ArcGIS, or there are tools to reproject data layers using like QGIS, and there are also options within Python and stuff too. Okay, and then like for example here, I'm saving that Web Mercator version of the layer out to a file. So this toFile method applied to a GeoPandas object can be used to save it to disk, and here I'm just saving it to a shapefile, which is a type of geospatial data layer file format. Let's see here. So this is just showing a plot where we're actually showing data, not just the boundaries. So this is the column is 2006. So this is the population 2006. So this is the column name, and then I'm using this blue-green color ramp, which is a named color ramp from Matplotlib. If you click on this link here, this lists out some example color ramps that are available in Matplotlib. Oops. Okay, cool. Now, yeah, so here's an example of creating a new column that gets stored in the table. Again, just like with pandas data frames, you can write to a new column without it existing before you call it. So you can create this new column kind of dynamically. So here I'm calculating population density by taking the population 2006 and dividing by the area in square miles. And then I'm just plotting that again with that new column and then a new color ramp. And then this quantiles is the classification scheme, so different ways to bin the data. There's things like equal interval, quantiles, mean standard deviation, things like that, natural breaks. So anyway, that's showing the population density. Yeah, and then what are we doing different here? So yeah, here we're adding in the ramp. Actually, no, I think that was right. Yeah, that's that. What are we doing differently here? Just using a different color ramp. I'm trying to remember what I did. Oh yeah, sorry. So here I didn't specify the scheme, so I got a different color ramp. That's why they look different than it did, than this one did. So it's a different ramp. Yeah, but anyway, here I'm using this. I'm adding a legend with some characteristics. So this accepts a dictionary. So the label is basically the legend title, and then the orientation is I have it horizontal as opposed to vertical. And this is the same thing. I just switched the orientation to vertical. So I'm just showing you how you can add in a legend there as part of the plot. Okay, so remember when we talked about Matplotlib, you can have multiple plots in the same space, and that you do that by having subplots or multiple axes or whatnot. So here I'm just using different classification methods to show this population density variable, so quantiles, percentiles, equal interval, and natural breaks. I'm saving those into different axes, so I have one plot that shows all these different breaks. And it's kind of interesting about this, just as a side note, is this actually shows like patterns that look very different. So you got to really think about how you represent your data using things like colors and sizes and whatnot, because you can manipulate it to maybe make things look like they're maybe more consistent than they really are, or not as different as they really are, or highlight what you want to highlight and kind of subdue what you don't want to subdue. So anyway, these are important decisions. So this is kind of issues in data visualization and digital cartography and thematic mapping. Okay, so here's an example where we have multiple layers in the same space. So we have one plot with one subplot. So the first thing I do is add in the counties here and with a legend. Then I plot just the boundaries above it. So, and then let's see, I read in a new layer. This is towns, and I plot those as points. So this is just showing a map layout with 3 layers: the choropleth collars for the density, the county boundaries, and then the points. All right, so that was some examples using GeoPandas. So in this next section here, we're looking at Rasteria, and again, this is mainly for working with vector data. Okay, so just a couple notes about how Rasteria works. So generally, when you make when you open a connection to a layer on disk, when you're done with it, you want to close it. So I didn't do that here. I commented that out because I am continuing to use it. But when you run the open function on a raster layer, whenever you're done using it, you generally want to close the connection. So that's just kind of a general rule of thumb. And here I'm just printing some information about this specific raster. So this is the name of the raster, its full path on the disk. 1, that's the number of bands, so this is a single band. It's a DEM, or a digital elevation model. This is the width, so basically columns. This is the height, so rows. This is the bounding box, so the left, bottom, right, and top coordinates, and these coordinates are going to be in the relative to whatever the coordinate reference system is, which in this case is a UTM coordinate system. It's UTM zone 17 north, so eastings and northings, and then .crs returns the European Petroleum Survey Group code, or EPSG code associated with the, in this case, UTM 17 north projection. Okay, so whenever you have a multiband layer, you can read in not all of, you can read in a subset of the bands if you want. Now, this is different than we typically do in Python, where index starting at 0. Instead, it starts at 1. So if you read in band 1, that's band 1. If you read in band 2, it's band 2, right? And then this is just printing it out as an array. So effectively, the difference here between open is basically making a connection to a file on your computer, and then closes that connection. What read does is it reads the data associated with that with the data on disk into an array, effectively like a NumPy array. So this allows you to treat it like a NumPy array, and you can do a lot of different operations on it. So that's the difference between open, which is basically making a connection to a layer, and read, which is reading the data into an array. Here I'm using matplotlib to just display that. So I'm using the imShow function, and I'm displaying that elevation data, which is now basically just a NumPy array, to show the distribution. So this is a DEM. Okay, cool. All right, and then this is just showing some different color ramps applied to that. So again, I'm just making a figure with 4 subplots, and I'm just mapping the elevation using different color ramps, just to show you some different color ramps. And again, there's a bunch of named color ramps that you can grab from like matplotlib and other tools. Okay, so that was a single band object, a digital elevation model. Here we're looking at a multi-band object. So here I'm making a connection to this Landsat 8 examples file, and then I'm listing some information about it. So here's the path to the object on disk. It has 7 bands, or 7 layers. Its width is 2018, so there's 2018 columns of data and 1,817 rows of data. This is the bounding geometry relative to the coordinate reference system, and this is the EPSG code for the reference system. So same as above, right? So again, if you do a read, that reads the data into an array, and a NumPy array, and if you don't give it an argument, it's going to read in all of the bands. So you're going to get a shape here in this case. So if we print the shape, it's 7, 1817, 2018, right? So this is the number of bands. The let's see, 18 was the was the number of rows, and then the number of columns. So channels, rows, columns. Now if I just pull in one band, then I get back a 2-dimensional array. So you don't really need channels if you only have one channel, right? So there's nothing to differentiate. That actually is a bit of an issue sometimes in Python, because some methods, and this applies to things like, when you're dealing like convolutional neural networks, it's going to expect a single band raster to be like it's going to three dimensions as opposed to 2. Sometimes you want the channels to be last as opposed to the first. So there are methods to make those types of reshaping manipulations. But here I'm just trying to show you the shape of the arrays that it generates. And so again, channels, rows, height, and then this is just rows, height when it's a single band. This is the 5th band, which is shortwave, band. Okay, so here I'm just plotting just a single band. You can see that here. This is 6, which is actually would be 7, right? Because now we're using NumPy indexing, so it starts at 0. So that's one band. This is showing the min and max of that band, and then the mean. There we go. You can use these sometimes to help with rescaling. So here I see that the mean's actually pretty low. So I just have the image saturated at a value of 50. So this is really washed out. This is less washed out, right? Okay, so what if you wanted to show multiple bands? So here I'm just drawing a couple different bands as a single band raster using different color ramps. So this is the blue channel, the green, the red, and then this is near infrared. Now, if you want to plot like a composite image, then generally we would do that, or generally I do that using the EarthPy library and specifically the plot RGB function. So to do that, you basically have to give it an array that represents the data, the mappings. So here we're doing 3, 2, 1, and again this is indexed starting at 1 instead of 0. So in this case, band 3 is red, band 2 is green, and band 1 is blue. So it's a simulated true color image. If you apply a stretch, it does a stretch, and this stretch clip is a parameter for the stretching. So excuse me. So anyway, this is a kind of standard simulate true color composite image there of this area over Vancouver from this Landsat 8 image. This is a mapping where band 4 is red, which is mapped to red. Band 3 is mapped to green, and band 2 is mapped to 1. So this is near infrared is red, red is green, and then green as blue. And then this creates these red-looking images where the vegetation and whatnot shows up as red because it reflects a lot of near infrared. And then lastly, this is showing an example where the shortwave is shown in red, the near infrared is shown in green, and then the green is shown as blue, which is a common composite used for like Landsat data. There's also this plot bands option, which is part of the EarthPy library. So this will make a separate plot for each of the channels or bands in a layer as a separate image here, so multi-axis figure or with multiple subplots here. And then here this is showing histograms for each of the layers. So you can kind of see the distribution of the digital number values in each of the layers there with the associated band names. Yeah, so anyway, I created an array of titles there, and then the histogram, and then plotted. And I just realized I was wrong about this. I think that actually does index starting at 0. Yeah, it does, because the first band is actually not blue, it's the edge. So these are actually do start indexing at 0 instead of 1. I apologize for that. I just realized that. Okay, cool. So the last section of this is on Whitebox Tools. Anyway, what I did here is just went through a series of examples that showed you how to do some different and like common operations and like geoprocessing, spatial analysis operations using Whitebox Tools. So I have a series of different layers on my disk here. Some of them are shapefiles or vector layers. Some are images or raster grids. I also have a table here. So I just am writing all those to variables, so I don't have to call the paths there. And then I'm setting an output folder for where I want to save my results. And I'm also setting this argument or parameter for Whitebox Tools, verbose to false, and that's so that it doesn't print a bunch of stuff. Now I did that because when I rendered this page, I didn't want to have a lot of like warnings and progress bars and stuff show up just to keep it cleaner. But if I actually am using Whitebox Tools, I prefer to leave this set to the default, which is true, because some of the text that it prints as it runs is useful, especially if it takes a while and you want to see the progress or whatnot. Okay, so running tools with Whitebox Tools is actually pretty easy. So what I'm doing in this first example is just doing a dissolve. So I'm using these watershed boundaries. I'm writing into the output folder and giving, so this is like string concatenation, so the output folder plus the new file name. Then I'm doing a dissolve using this ICU field, and then this is a snapping parameter, has to do with like snapping of vertices. And then once that runs, I just read it back in using GeoPandas and then plot it with Matplotlib. So this is we took these watershed boundaries and then we collapsed them into these more general boundaries. So that's a dissolve. So it's really easy. Basically, this is the function from Whitebox Tools, the input, the output, and then some other parameters like the dissolve field. Here I'm doing a table join. So actually, this is not a Whitebox Tools example, but I just wanted to show you how to do a table join. So you might remember that whenever we work with GeoPandas, you can do table joins using like a common field or key, and that's done with the merge function. So here I have a table of I have watersheds, and then I have a table of information about those watersheds. Now, so this is this harvest table, and then this is the watersheds there. So here I'm just remapping so that the same field has the same name in both, and then I'm doing a join to get that back, and then I'm plotting on it. And now I'm actually realizing that that's a weird variable name, because this is not watersheds. These are the West Virginia counties. So I'm not sure why I call it that. So anyway, these are the West Virginia counties. This is deer harvest data from like hunting season on a county by county basis. And then to do this renaming in the West Virginia counties, I want the name column to be changed to county. So just renaming the column. I'm doing it in place. And then I basically join that data based on the counties layer. And here you can just see the result. So it just adds on these layers that relate to deer harvest. So there's the geometry. So that was the end of the original data frame. And then these are the added on layers there. And then I'm just plotting, in this case, the total deer harvest, which is this field here. So you can see the number of deer that are harvested. Okay, here's a simple clip. It's arguably one of the most commonly used geoprocessing operations. So here, clip basically works via this tool. It's called clip, right? So, I'm taking this this table here, and I'm pulling out only this. So this is the result from above, and I'm just pulling out the counties that are in the Eastern Panhandle region. There's just 3 counties there. And then I'm writing that out to disk to a new file called ep.shape. And then I'm writing the file path to a new variable, and then I'm using the clip tool. So here I'm clipping this West Virginia towns layer using this new Eastern Panhandle data, and I'm writing it out as EP towns, and then I just plot it here, or read it back in, and then plot it with Matplotlib. So these are those 3 counties that I extracted out, and then I clipped out only the points that fell within them, which is just that point, right? So that's an example of a geospatial clip on a vector features. This is an example of clipping a raster. So in this example, pardon me, we want to do clip raster to polygon. So you feed it in the raster you want to clip. In this case, it's an elevation raster. And then watersheds, which is the boundary we're going to use to do the clipping. This is the name of the output, and then maintain dimensions, I put false, but if you set that to true, it maintains the number of rows and columns that was in the original data. It just puts null values in them. And then here I'm plotting it as Matplotlib using 2 subplots. So here's the mass version of this data set. And you can see that they're not the same extent there. So this is a smaller chunk of it. It's like down in this area. This is a geospatial intersection. So here I'm intersecting watersheds and county boundaries and writing that out to file. I do this a lot in here, just as again in these examples. So I have an output folder variable, and then I just concatenate onto it the name of the output file. So it's just kind of quicker than having to write out the entire file path each time. And then here again, I'm just plotting it. So here are the watersheds, and here are the watersheds sliced up along county boundaries. Resample raster basically means to change the cell size. So this is an example of doing that. So we're resampling the elevation data. We're writing it out to a file called elevation re in our output folder. We're changing the cell size to 100, so it'll be 100 by 100 meters, or whatever the map units are, which are meters in this case. And then the method is CC, which means cubic convolution. And then I read in the original layer and the resampled output, and then get the height, which is the number of pixels. So basically the original one had 1923 rows of data, and then after it was resampled, now it has 577 rows. Okay, this is another example kind of related to digital terrain data. So this is creating a hillshade, and specifically a multi-directional hillshade. So what that means is it uses multiple sun positions to generate the shaded relief surface. So this is the input elevation. This is the output layer. This is the altitude or the height of the sun above the horizon. The Z factor is none, so there's no like exaggeration or converting feet to meters or something. And then we read it back in, and then we plot it. So there's an example of a multi-directional hillshade. This is a topographic position index. So again, you just feed it elevation, name and output, and then the filter XY, it's just based on a moving window. So it's basically the cell value minus the mean of its neighbors, or the mean of all the values in the local window. So anyway, the size of the window impacts the pattern and how generalized it is and whatnot. And then again, just read it in, and then plot it using matplotlib. So in this case, the higher values are like high topographic positions like ridges and whatnot, and the low values are lower positions like valleys and depressions and whatnot. This is an example of a landform classification. Note that one thing that's kind of difficult with matplotlib, in my opinion, is mapping colors to categories. So anyway, I pulled some documentation here that explains how to do that. So that's what a lot of this code is, just applying colors. So this is an example of a landform classification, and a lot of this is just mapping the colors. And you can read through that example, and also there's examples here too that explain it in more detail. This is an algorithm that searches for ridge lines. In this case, I felt like it didn't do a very good job, but that's what it's for. So anyway, give it an elevation surface, and it writes back a binary ridge versus not ridge file. I believe it's binary. All right, this is like raster math type operations. So this equal to, you can find all the cells that are equal to a value. So here I have a land cover data set, and I found all the cells that have a value of 41, which is the code for deciduous forest, and then I get a map of deciduous forest versus not deciduous forest. Here's greater than, so greater than or less than a value, so like threshold. So here I'm getting back all the elevations that are greater than 600 meters will be coded to 1, and all the elevations that are 600 meters or lower will be coded to 0. So that's our binary elevation output there. Extracting values at points is a common pre-processing step for like creating data sets for like machine learning and whatnot. So in Whitebox Tools, the extract raster values at points tool can do that. So here you can basically get the you give it a grid, points, and then whether you want to output it to like a text file or to a spatial file. This is similar, but instead of collecting data at points, this is data by zones. So here we're doing zonal statistics. So the first thing we have to do is convert our zones into rasters, because this only works with raster overlay. So we are basically converting our watersheds into rasters, where each watershed, as designated by its FID, gets a different code. And then we use the raster version of the watersheds and the elevation data to get back a mean elevation. So in this case, all the cells that occur in the same watershed are going to have the same cell value, which is the mean elevation in that watershed. Whitebox Tools also has some functions for working with LiDAR data. So, for example, there's multiple things you can do, but these are just some common examples. So this filter LiDAR classes allows you to filter out points that only from a specific class, right? So you could filter out, for example, the ground points only, or the not ground points, or the outlier points, or something. So that basically allows you to decide what class codes it is that you want to keep. So the way I set this up, this would return just the points that represent ground returns or classified ground returns. This is an example of rasterizing LiDAR. So this is a function to create a digital surface model. So you can set a resolution. I believe the radius has to do with the searching. Actually, I'm not really sure what that does. So anyway, this is a function that generates a digital surface model from a point cloud. This this is a way to interpolate a point cloud using inverse distance weighting, and these are parameters associated with that. And here I'm interpolating specifically the intensity data. So here's those results. So this is your digital surface model, and then this is your intensity image. So return intensity image. And then here I'm doing a couple other things. So I create a hillshade. So here's our digital surface model, but this time I'm just creating it using the ground point, so it's a DEM as opposed to a DSM. I'm creating a multi-directional hillshade from that DEM, and then I'm subtracting the DEM from the DSM to get a normalized digital surface model, which represents height above the ground level, and I plot all those back here. Okay, so anyway, that's an example of some tools for doing GIS stuff in an open environment using Python. Specifically, we looked at using GeoPandas, mainly for displaying and working with vector data, Rasteria and EarthPy for mainly working with raster data and images and multiband images, and then doing a lot of key geoprocessing operations using Whitebox Tools. I really like Whitebox Tools. It's really easy to use and it's well documented. If you go to this documentation page for Whitebox Tools, there's really good documentation of all the different tools that are available. Again, there's over 400 tools available, so I just showed a few examples, but there's lots of other things you can do with this tool.